Hello and welcome to our presentation on portable versus traditional MRI. I'm Jason.
I'm Catherine.
I'm Mia.
Let's begin. First off with our summary slide, this project compares low-field portable MRI with high-field traditional MRI. While a low-field MRI has degraded image quality, it can be used in regions without specialized facilities or in other cases where traditional MRI is unfeasible. In this project, we do the following simulations to compare the two modalities. First off, we have a qualitative comparison demonstrating that with all physical properties being held equal, image quality is severely eroded when the phantom is imaged with a low-field scanner. However, engineering and processing can reconstruct a viable image despite the low-field scan. Secondly, quantification of the first comparison demonstrating that compensated low-field MRI preserves usable signal and structure, but a naive 0.1 Tesla does not. This highlights the need for optimized reconstruction strategies. And thirdly, we do a simulation of a qualitative comparison of the T1 and T2 weighing reconstructions for the 3 Tesla and the 0.1 Tesla MRI comparisons. Signal and structure are preserved in the 3T case, but are lost in the 0.1T case, which requires significant reconstruction to recover. I'm good.
So now just to cover the basics of MRI physics, the hydrogen protons in the subject are first aligned using a strong magnetic field. Then an RF pulse knocks these protons out of alignment. After the RF pulse ends, the protons relax back into alignment, and during this relaxation, the protons emit energy signals that are captured by the computer and translated into a detailed image. For the hardware, we'll cover the 3 main systems. The core of the MRI apparatus consists of a large magnet which generates the field for nuclear polarization. The majority of MRI systems use a superconducting magnet since it provides fields of high strength and stability, but these require liquid helium cryogenic systems to keep at a low operating temperature. This makes the system bulky, so for the portable MRI machines, we typically see the use of permanent magnets of either iron or air core, since these are the most cost-effective for field strengths below 0.3 Tesla. The radio frequency coil system is important for stimulating the spin systems, and the magnetic field gradient system consists of gradient coils, which are used to produce near-linear magnetic gradients in various directions. These are the essential element for spatial encoding and are also responsible for encoding dynamic information related to flow, diffusion, or modulation of magnetization for spatial tagging. Go back a slide, and you can see the hardware block diagram overview with the computer, the main magnet apparatus, and the transmit and receive systems. The fundamental equations for MRI, we'll start with these 3. The first one is the block equation, which represents the motion of the magnetization vector of uncoupled spins, where here gamma is the gyromagnetic ratio, H is the effective field, M naught is the equilibrium magnetization, and T1 and T2 are the relaxation times. Second equation is our spatial frequency vector, which is used to express our signal. Here, GT prime is the time-dependent spatial encoding gradient, which imparts differing phase shifts to spins at different spatial locations. This equation shows that the time variation of the spatial frequency vector is determined by the integral over the gradients. And the third equation shows that at each point in time, the received signal is the Fourier transform of the object evaluated at the spatial frequencies above. Thus, the gradients control our position in K-space. The design of an MRI pulse sequence requires us to efficiently cover enough K-space to form our image.
For the basics of the portable MRI, the portable low-field MRI systems are those operating with a magnetic field between 10 and 100 millitesla. They utilize permanent magnets that do not require cooling and are light enough to move. While the signal-to-noise ratio of the portable MRI system is worse than that of a traditional high-field system, as depicted in the image to the left, the traditional system has a large fringe field and requires strict safety parameters. On the other hand, the portable system can be utilized at a patient's bedside when traditional MRI is contraindicated or in rural communities that have no access to advanced facilities with high-field MRI. Next slide, please. For the direct comparison of low to high-field MRI, the low field is the 0.1 Tesla and the high field will be 3 Tesla for our model. On the software and the large difference in field strength shapes almost everything else about it. On the software side, portable MRI relies heavily on AI-based reconstruction to compensate for its lower SNR. High-field MRI uses established Fourier and parallel imaging methods with much higher baseline signal. As a result, portable MRI provides lower resolution, lower SNR images, good for detecting major findings like hemorrhage or midline shift, while 3 Tesla MRI delivers full diagnostic image quality across all body regions. Clinically, portable MRI is ideal for ICU imaging, bedside use, stroke triage in rural or resource-limited settings, and the 3 Tesla scanner supports comprehensive hospital diagnostics and advanced research applications. The costs are also very different. Portable systems run about $50,000 to $350,000, while the 3T MRI scanners cost about $1.5 to $3.5 million, not including room construction, which is needed for a higher field system. The infrastructure and operating costs thus follow the same pattern. Overall, the portable MRI expands access to imaging, while 3 Tesla MRI provides the gold standard diagnostic quality needed in major hospitals. Next slide, please. This is how our first simulation works, the image quality comparison. First, we start with the Shep Logan Phantom. This object never changes with same FOV, same matrix, same sampling. So any differences in the images come only from the B0 or the compensation steps. Next, we model the 3 Tesla baseline. All we do is add a small amount of realistic 3 Tesla K-space noise. That gives us the clean, high SNR reference image you see in the top right. Then we create the naive 0.1 Tesla case by lowering the field strength but keeping everything else the same. Because the signal scales with B0, the noise effectively becomes about 30 times larger. That's why the bottom left panel looks so degraded. It shows the raw physics penalty of going to a very low field without adjusting the protocol. Finally, we show what a real low field scanners actually do. We reduce effective noise penalty, apply moderate low pass filtering, average multiple acquisitions, smooth the image, lightly enhance the edges, and stretch the contrast. The result is the bottom right panel, a low field image that's still not as sharp as the 3 Tesla one, but clearly readable and clinically usable. So the single figure walks us through the whole story. 3 Tesla gives high SNR, the naive 0.1 Tesla collapses under the physics, and the compensated 0.1 Tesla shows how engineering and processing bring low field MRI back into a usable range.
Okay, so to follow up this initial comparison simulation, we quantified the differences between the images produced by the 3T case and the 0.1T case, which represents the portable MRI. We begin by using the exact Shep Logan Phantom used in the visual simulation so that all comparisons are based on a known ground truth. We will use the 3T, 0.1T naive, and 0.1T compensated images that were generated in simulation 1. We will then define regions of interest, a central ROI representing true signal and a corner ROI representing background noise. Then we compute the signal-to-noise ratio for each image and the contrast-to-noise ratio for each image by measuring the contrast between the central ROI and the background region. We then quantify the edge sharpness by computing the gradient magnitude at locations where the true phantom has edges and compare the mean gradient values between 3T and 0.1T images. This measures how well the field strength preserves boundaries. We then compute the reconstruction accuracy by comparing each image directly to the phantom, and we create a 4-panel comparison figure and repeat this for naive and compensated low-field images. Next slide, please. The results of this quantification were as follows. Starting with SNR, compensation improves SNR, but 0.1T still achieves only about 50% of 3T's SNR, while naive performs far below high-field MRI. Next is CNR, contrast to noise ratio. Naive 0.1T loses almost all contrast, while compensated 0.1T preserves about 30% of 3T's CNR. For edge sharpness, compensated 0.1T edges are close to 3T, but naive produces artificially high gradients, not reflective of true structure. Finally, looking at reconstruction error versus ground truth phantom, compensated 0.1T retains structure, but remains about 6 times less accurate than 3T. Naive 0.1T is significantly worse, fundamentally diverging from 3T image quality.
So, for simulation 3, we compared the T1 and T2 weightings for the 3 Tesla and 0.1 Tesla cases. The simulation logic is as follows. First, defined the image geometry and MRI system parameters, and then generated the anatomical phantom and segment tissues. I used the same initializations from our simulation 1 to keep it consistent. Then assigned the tissue T1 and T2 relaxation values at high and low field and built the pixel-wise T1 and T2 maps. Then using the spin echo equation, I computed the spin echo signal using the TR and TE values taken from the standardized textbook ranges. Then added realistic MRI noise in K-space, and then finally had to clinically realistic, though somewhat optimistic, low field reconstruction of the 0.1 Tesla cases. Because of the noise, the signal to noise ratio was too low for the naives. You can see the SNR values below here as well. For our results, the T1 and T2 cases are consistent with what we'd expect to see, with gray matter being darker, white matter brighter, and cerebral spinal fluid being very dark for the 3T MRI case. And then same for T2, which emphasizes fluids and pathology. The CSF is brighter, gray matter is slightly brighter, and the white matter is darker. For the 0.1 Tesla portable MRI, the image reconstruction for both T1 and T2 weightings is poor with a low SNR, which requires the clinically realistic low field reconstruction to increase the SNR and recover the signal/structure.
Okay, so key takeaways. Simulation 1 showed qualitative evidence of severe image degradation as SNR decreases with reduced magnet field strength. The compensated results demonstrate that despite the loss in field strength, post-processing and acquisition strategies can substantially improve image quality. Simulation 2 showed compensated low-field MRI recovers enough signal and structure to be usable, but naive 0.1T cannot approximate 3T in any metric. This shows why portable MRI requires optimized reconstruction strategies. And Simulation 3 showed T1 and T2 weightings for conventional 3T MRI are recoverable, but 0.1T portable MRI requires low-field reconstruction to recover any signal. Next slide, please. So some potential future outlooks for portable MRI. AI-driven reconstruction. Deep learning will help overcome low SNR and resolution in portable MRI, including translating low-field images into high-field-like quality. Expanded clinical utility. As reconstruction improves, portable MRI can expand into more clinical settings, though larger-scale multi-site data sets are still needed for validation. Integration into routine care. With better cost, size, and reconstruction quality, portable MRI could become a bedside screening tool that complements rather than replaces high-field MRI. Next slide, please. Thank you, and these are our references.